Hello everyone, I am Mrs. Sonia Singh, working as Digital Science in Army Public School, Colourful. Today in this video, I'll be talking about Class 10th chapter Human Eye and the Colourful World. The topics that I'll be taking in this video is about prism, the refraction of light through prism, its deviation, how it deviates from its path, the dispersion of light. Then we'll be talking about various phenomena related to dispersion of light. We'll be talking about atmospheric refraction and the phenomena related to it, scattering of light, Tyndall effect. So the various phenomena that we'll be talking about, like formation of rainbow, how is a rainbow formed? We'll be talking about the twinkling of stars and why do planets not twinkle? We'll also be talking about delayed sunset and advanced sunrise. Why sky is blue in color. Then we'll be talking about why signals are red in color. We'll be also be talking about the activity explaining how light gets scattered, and then the reddish orangish color of the sun during sunrise and sunset. So all these topics we are going to take in this chapter. So in the previous chapter you studied about refraction of a light through a glass slab. I hope you remember that. In this chapter we will be talking about the refraction of light through a prism. So let's consider a glass surface which is bounded by three glass slabs from three sides. Three glass slabs from three sides and from two sides by triangular surfaces. So this forms a prism. These surfaces are inclined to each other, and these surfaces, these lateral surfaces which are the rectangular glass slab, they form an angle. This angle is very particular about a prism, which we call as angle of prism. So all the refraction, whatever type of refraction or deviation of light takes place, it is all due to this angle. To understand this, let us perform an activity related to glass prism.
So we are going to perform an activity to show that how a ray of light gets refracted through a prism. So this is a prism. As you can see that it is bounded by three rectangular surfaces and two glass bases. So for this, what are we going to do? We are going to fix a white paper on a drawing board using drawing pins. Then we'll place the glass prism on it in such a way that it rests on its triangular base. Now trace the outline of the prism using a pencil. So we'll be tracing the triangle now. We will complete the boundary by using pencil and scale. Now we will draw perpendicular on one side of this structure, as we have to make an incident ray falling on this surface. So for this we need to make a normal, that is 90 degrees. So this is the 90 degree here. From here we are going to make incident ray, and we will take the angle of incidence as 60 degrees. So this is the normal. Now we'll count from here. So let's count 10, 20, 30, 40, 50 and 60. So this will be the angle of incidence. Now we'll join these lines. We'll draw normal, that is the 90 degree to this surface, and incident ray, that is making an angle of 60 degree with the normal. So this is angle I equals to 60 degree. Now what we are going to do, we are going to now place oil pins on this incident ray. So we'll take two oil pins and place on the incident ray. In this manner, we're going to do it. Now what we have to do, we'll place back the prism on the boundary that we had made, and then we'll try to look at the images of these two pins from the other lateral surface of the prism, from the other side, from this side. So I'll be placing the pins right in front of the images that will be observed from the other side of the prism. So I'll be fixing the pins now. I'll be showing you how I'm going to fix it, how in front of the two images of the two pins I'm going to fix the other two pins so that they are absolutely linear in a straight line. We should make sure that the two pins that we are placing in front of the images of the other two pins, it should be straight. It should be one behind the other. So I'll be showing you how it looks. Just look at the images. If you can see in the prism, look at the images. The images of these two pins are visible from the other side, and right in front of the images I have placed these two oil pins so that they all are in a single straight line. So can you see it? Okay, so now we are going to remove these pins and mark the position of these two pins with the help of a pencil. We'll remove the prism and join these two dots with the other surface of the prism. So this will be the emergent ray. This is the emergent ray that have emerged out of the prism after suffering refraction. We'll draw a normal at this point also, as we have studied under the law of refraction that the incident ray, the normal and the refracted ray all lie on the same plane. So as it is a refracted ray, which is the emergent ray, so we'll draw a normal, we'll measure it with the help of a D. So we'll join the dots, and this will be the normal to the other surface of the prism. We'll measure the angle now, angle of emergence. This is the first, we'll draw the refracted ray that has been refracted internally. So this is the refracted ray. Now we'll measure the angle of emergence now. So we'll measure from, we'll place the D in this position and we'll measure from 90. That will be the 0, 10, 20, 30 and 40. So it's exact 40 degrees. So angle of emergence is equals to 40 degree. Angle E is 40 degrees. Now what we'll do, we'll trace back the incident ray and the emergent ray, showing that how much it has got deviated. You can look at the path of the emergent ray and the incident ray. So this is the angle A of prism, which is 60 degree, as we know that this is an equilateral triangle, so all angles are of 60 degree. So we'll now trace the incident ray, which would have been the original path of the light if prism wasn't there, and we'll trace back the emergent ray as well. I'll make the line a little darker so that it is visible to you. So this is the emergent ray. Okay, So where these two rays meet, that point makes the angle of deviation. Now we'll measure this angle of deviation with the help of D now. So in this position we are going to place the D and we'll measure now this angle. So this is exactly 40 degree. So here we've got all the angles. So we'll write down these angles now. Angle I, we've taken 60 degree. Angle E is 40 degree. Angle A, that is 60 degree, that's given. And angle D is 40 degrees. So we have a relation also with these four angles. So it is like angle I plus angle E should be equal to angle A plus angle D. So let's write down the values now. Angle I is 60 degree. So you can see we have taken 60 degree. Angle E is 40 degrees. Angle A is 60 degrees and angle D is 40 degrees. So now we'll find out the sum. 60 plus 40, 100. Here also 60 plus 40, 100. So our experiment is perfect. We have measured, taken all the angles properly.
While doing this activity, you must have observed that as the incident ray it passes through one surface of the prism, it bends towards normal. Here you may observe that the incident ray is coming from a rarer medium, which is air, and it is passing into a denser medium, which is glass. Right? Now, when the light ray moves from rarer medium to a denser medium, it bends towards normal. I hope you remember that. And as you see, when it is bending towards normal, the light ray is bending toward the base of the prism. So now this ray is called as the refracted ray. Now this refracted ray has to move out from the glass to the air, that is from the denser medium to the rarer medium. Now when the light passes from the denser medium to the rarer medium, the light ray will bend away from the normal. So this is how, when the light ray is bending away from the normal, that ray is called as the emergent ray. Now here you saw that the incident ray was extended and the emergent ray was also extended, which formed the angle of deviation. Now this angle of deviation shows the degree to which the light ray got deviated from its path. But when you compare the refraction of light through prism and through glass slab, refraction through a rectangular glass slab, it formed the emergent ray is actually parallel to the path of the incident ray. It has not got deviated from its path. The path is same, but there is slight lateral displacement from its path. But in case of prism, because of angle of prism, it has got deviated. The light ray initially was moving in upward direction, and when it emerged out of the prism, it got deviated, means now it is moving in the opposite direction. So now can you notice the difference between the refraction of light through a glass prism and refraction of light through a rectangular glass slab? Now you must have observed and appreciated the spectacular color of the rainbow. Now those colors may have come from the white light of the sunlight. So we consider sun as the biggest natural source of white light. Now, but how this white light gives 7 colors? So this is explained by prism. You may observe when the white light it falls on the prism in such a way that it forms 7 colors on the other side, it actually splits into 7 colors. Why? Because of the angle of the prism, because of the peculiar shape. Now, this peculiar shape of the prism shows various phenomena. So we are talking about this phenomena in which the white light gets split into 7 colors. So this phenomena of splitting of white light into 7 colors is called as dispersion. Now the question is, why do white light get splitted? Why does it get dispersed? Why dispersion takes place? This is due to difference in the wavelength of different colors. When you note down the different colors, you can remember the colors in the form of acronym called as VIBGYOR. You can see that violet is the lowest one, then indigo, blue, green, yellow, orange, and red. It is in this form, right? Now, these 7 colors, which are in visible range, they have different wavelengths. The wavelength of violet color is smallest and the wavelength of the red color is the longest. So the difference in the wavelength of these lights have different refractive indices when they pass from the prism. So due to different refractive indices, their bending is also different. So the the violet light, which has the very least wavelength, it bends the most, right? Because it has greater refractive index. And the red light, which has the longest wavelength, it bends the least. So that is why there is dispersion seen in the prism. This phenomena was observed by Isaac Newton. Isaac Newton, he tried to refract light and various colored light through different transparent media. When he tried it with glass prism and he tried the white light, he observed that the white light got dispersed. So he thought, okay, the light, the color which is being observed, that may be of the prism. So he tried the same thing by taking different prism, and he also thought maybe it could be split into some more colors. So instead of taking just one prism, he took one more prism. But he observed that the number of colors was same, that was 7. So he concluded that the white light could be split into only 7 colors. And the white light is not of the prism. The white light that is of the sun, the color which is it getting split into is not of the prism. It is actually the white light. He took one upright prism and along with it, he took an inverted prism. And he passed the white light through the upright prism, and the 7 light that got dispersed from the white light, he passed those 7 lights through the inverted prism, and he observed that through the second prism, all the white light got recombined. So this was the recombination experiment done by Isaac Newton. So which proved that the white light has 7 colors. So any source of light which consists of 7 colors is the white light. So he named this experiment as recombination of spectrum of white light. A rainbow is a natural spectrum formed in nature where splitting of white light takes place. Now, there are some fixed conditions where you can see rainbow. So what are those conditions? Sunlight should be available. It should be raining or drizzling. Sunlight should be at the back of the observer and rain should be in front of the observer. The raindrop will work as a prism. So how does a prism work? It actually disperses the white light. So as the white light from behind, when it enters the raindrop, it gets split, it gets refracted and split, dispersed into 7 colors. Now instead of moving out of the raindrop, it actually gets internally reflected, which is a phenomena of refraction only. So light ray gets internally reflected and a rainbow is formed.
You might have observed the apparent random wavering or flickering of objects seen through a turbulent stream of hot air rising above a fire or a radiator. The air just above the fire becomes hotter than the air further up. The hotter air is lighter, that is less dense, than the cooler air above it and has a refractive index slightly less than that of the cooler air. Since the physical conditions of the refracting medium, that is air, are not stationary, the apparent position of the object as seen through the hot air fluctuates. This wavering is thus an effect of atmospheric refraction. The twinkling of stars is a similar phenomena on a much larger scale. Let us see how we can explain it. The twinkling of a star is due to atmospheric refraction of starlight. The starlight, on entering the Earth's atmosphere, undergoes refraction continuously before it reaches the Earth. The atmospheric refraction occurs in a medium of gradually changing refractive index. Since the atmosphere bends starlight towards the normal, the apparent position of the star is slightly different from its actual position. The star appears slightly higher than its actual position when viewed near the horizon. Further, this apparent position of the star is not stationary but keeps on changing slightly since the physical conditions of the Earth's atmosphere are not stationary, as was the case in the previous case. Since the stars are very distant, they approximate point-sized source of light. As the path of rays of light coming from the star goes on varying slightly, the apparent position of the star fluctuates and the amount of starlight entering the eye flickers. The star sometimes appears brighter and at sometimes other time fainter, which is the twinkling effect. Now let us talk that why don't the planets twinkle? The planets are much closer to the Earth and are thus seen as extended sources. Let us consider a planet as a collection of a large number of point-sized sources of light. The total variation in the amount of light entering our eye from all the individual point-sized sources will average out to zero, thereby nullifying the twinkling effect. So this is why the planets do not twinkle. Now let us talk about another phenomena related to atmospheric refraction, that is advanced sunrise and delayed sunset. The sun is visible to us about 2 minutes before the actual sunrise and about 2 minutes after the actual sunset because of atmospheric refraction. By actual sunrise, we mean the actual crossing of the horizon by the sun. Now, this figure shows the actual and apparent positions of the sun with respect to the horizon. The time difference between actual sunset and the apparent sunset is about 2 minutes. The apparent flattening of the sun's disk at sunrise and sunset is also due to the same phenomena. The interplay of light with objects around us gives rise to several spectacular phenomena in nature. The blue color of the sky, the color of water in deep sea, the reddening of the sun at sunrise and the sunset are some of the wonderful phenomena we are familiar with. In the previous class, that is in the ninth class, you have learned about the scattering of light by colloidal particles. The path of a beam of light passing through a true solution is not visible. However, its path becomes visible through a colloidal solution where the size of the particles is relatively larger. The Earth's atmosphere is a heterogeneous mixture of minute particles. These particles include smoke, tiny water droplets, suspended particles of dust, and molecules of air. When a beam of light strikes such fine particles, the path of the beam becomes visible. The light reaches us after being reflected diffusely by these particles. The phenomena of scattering of light by the colloidal particles give rise to Tyndall effect, which you have already studied in class 9th. This phenomena is seen when a fine beam of sunlight enters a smog filled room through a small hole. The scattering of light makes the particles visible. Tyndall effect can also be observed when sunlight passes through a canopy of a dense forest. Here, tiny water droplets in the mist scatter light. The color of the scattered light depends on the size of the scattering particles. Very fine particles scatter mainly blue light, while particles of larger size scatter light of longer wavelengths. If the size of the scattering particles is large enough, then the scattered light may even appear white. The molecules of air and other fine particles in the atmosphere have size smaller than the wavelength of visible light. These are more effective in scattering light of shorter wavelengths at the blue end than light of longer wavelengths at the red end. The red light has a wavelength about 1.8 times greater than blue light. Thus, when sunlight passes through the atmosphere, the fine particles in air scatter the blue light, which is having shorter wavelength, more strongly than red. The scattered blue light enters our eyes. If the earth had no atmosphere, there would not have been any scattering. Then the sky would have looked dark. The sky appears dark to passengers flying at very high altitude, as scattering is not prominent at such heights. You might have also observed that danger signals lights are red in color. Now, why is it? The red is least scattered by fog or smoke. Therefore, it can be seen in the same color at a distance. Have you seen the sky and the sun at sunset or sunrise? Have you wondered as why the sun and the surrounding sky appear red? Let us do an activity to understand the blue color of the sky and the reddish appearance of the sun at the sunset or sunrise. Activity to understand the blue color of the sky and the reddish appearance of the sun at the sunrise or sunset. A source of light is placed at the focus of the convex lens to give parallel beam of light. A beaker with water, a cardboard with slit, a convex lens, and a screen are arranged as shown. Add sodium thiosulfate and concentrated sulfuric acid into the beaker and stir well. Pass the beam of light and observe the solution and the screen. We find fine microscopic sulfur particles precipitating in about 2 to 3 minutes. As the sulfur particles begin to form, we can observe the blue light from the sides of the beaker. This is due to scattering of short wavelengths by minute colloidal sulfur particles. Observe the color of the transmitted light from the fourth side of the glass tank facing the circular hole. It is interesting to observe at first the orange-red color and then bright crimson-red color on the screen. This activity demonstrates the scattering of light that helps us to understand the bluish color of the sky and the reddish appearance of the sun at the sunrise or the sunset. Light from the sun near the horizon passes through thicker layer of air and larger distance in the Earth's atmosphere before reaching our eyes. However, light from the sun overhead would travel relatively shorter distance. At noon, the sun appears white as only a little of the blue and violet colors are scattered. Near the horizon, most of the blue light and shorter wavelengths are scattered away by the particles. Therefore, the light that reaches our eyes is of longer wavelengths. This gives rise to the reddish appearance of the sun. Now we'll discuss some important definitions from this chapter. Prism. Prism is a transparent optical element which refracts light, having at least two faces with an angle between them. Angle of a prism. The angle between the opposite faces of the prism is called as angle of prism. Angle of deviation. When the light ray is allowed to pass through the prism, it makes the emergent ray bend at an angle to the direction of the incident ray. This angle is called the angle of deviation for the prism. Dispersion of white light. When white light is passed through a glass prism, it splits into its spectrum of colors in order like violet, indigo, blue, green, yellow, orange, and red. And this process of white light splitting into its constituent colors is termed as dispersion. Recombination of spectrum of white light. When white light is passed via prism, dispersion of light happens. The dispersed light that was produced will revert to white light when another prism is held inverted. It is known as the recombination of spectrum of white light. Atmospheric refraction. Atmospheric refraction is the shift in apparent direction of a celestial, that is like stars and planets, object caused by the refraction of light rays as they pass through Earth's atmosphere. Tyndall effect. The phenomena of scattering of light by particles in a colloid or in a very fine suspension is called Tyndall effect. Now we'll recapitulate what all we have done in this chapter. We all talked about prism and the angle of the prism due to which the deviation of light takes place. We also talked about discussed about the activity that showed the path of emergent ray, as you can see here, and how we can trace the emergent ray with the help of this activity and calculate the angle of emergence, angle of deviation by tracing the light ray, and we also proved the relation. We talked about dispersion of white light into 7 colors, that is into violet, indigo, blue, green, yellow, orange, and red. Their dispersion due to difference in their wavelengths. We also talked about the phenomena related to dispersion of light, that the rainbow formation in nature, that was due to the raindrop working as a prism in which refraction and all took place. We talked about atmospheric refraction, its phenomena related to atmospheric refraction, the twinkling of stars. We discussed the advanced sunrise and a delayed sunset, which is another phenomena of atmospheric refraction. We also discussed why planets do not twinkle. We discussed the activity related to Tyndall effect, the scattering of light to explain the blue color of the sky, and the orangish reddish color of the sun during sunrise and the sunset. We discussed about why the color of the sky is blue. the atmosphere, the color of the deep blue sea, and why the sky appears black to the astronauts, the red color of the signal, why the danger signs are red in color, the reddish orangish color of the sun during sunrise and sunset due to the scattering of light. Now we'll discuss some important questions related to this chapter, questions related to the examination point of view. The first question is, why is red color selected for danger signal lights? It is due to the longer wavelength of the red color. It is scattered the least. The next question is, what is meant by spectrum of white light, and how can we recombine the components of white light after a prism has separated them? The spectrum of white light, what it means? The 7 colors of white light. And how can we recombine it? By keeping another prism in the inverted form. The next question says that explain why do the planets not twinkle but the stars twinkle. Now, why do the planets not twinkle? Because they are nearer to us, nearer to the earth, and they are considered as extended source of point-sized objects, and stars are considered as point-sized objects. So their refraction is almost nullified. The twinkling effect is nullified. Next question is, what is dispersion of white light? And what is the cause of such dispersion? Dispersion means splitting of white light into its 7 colors. And what is the cause? Difference in the wavelengths and the angle of the prism. The next question is, the sky appears dark instead of blue to an astronaut. State its reason. It's very simple, because there is no atmosphere to scatter light there. That is why the sky appears dark to the astronauts. Next, name the type of particles which act as prism in the formation of rainbow in the sky. And this is the simplest question. It is the raindrop. Next, name the atmospheric phenomena due to which the sun can be seen above the horizon about 2 minutes before actual sunrise. This is the phenomena related to atmospheric refraction. Next is, why does the sun appears reddish at sunrise? Because during sunrise, the sun is near the horizon and the sunlight has to pass a thicker atmosphere and a longer distance. So red light reaches there first. That is why. Now you have to arrange the constituent colors of white light in descending order of their wavelengths. That means first the longer, that is the red, then orange, then yellow, then green, and then it is blue, indigo, right? So in this form. Next is, you have to name the 3 phenomena of light responsible for the formation of rainbow in the sky. So what happens in the raindrop? First the refraction, then dispersion, and then total internal reflection, due to which a rainbow is formed. I hope you understood this chapter. This is the phenomena. I hope you understood. So thank you. For any queries, you may contact me through online class. Thank you so much.